10:50 in the morning, January 10th, 1954. The pilot of British Overseas Airways Corporation flight GALYP was mid-sentence on the radio when the transmission cut. A few seconds later, metal debris fell into the Tyrrhenian Sea from 27,000 feet. 35 people were on board. None survived. That aircraft was a de Havilland Comet, registration GALYP, the first commercial jet airliner to enter passenger service. It was almost exactly a year old. 88 days later, a second comet, GALYY, left Rome for Cairo. 33 minutes into its climb, the radio went silent in the same manner. The wreckage came down near the island of Stromboli, killing 21 more people. 2 aircraft of the same type had broken apart in flight, on nearly the same route, within 3 months. In response, the British government grounded the global comet fleet indefinitely. The official inquiry into these crashes proved that in 1954, the aerospace industry lacked the engineering language to understand the machines it had already certified for flight. In the early 1950s, every other airliner was a slow, loud propeller aircraft. The Comet, by contrast, cruised at more than 400 miles per hour at 27,000 feet, flying well above the weather. Passengers experienced a cabin environment so quiet and smooth that they wrote letters about how they could not feel the engines. This comfort was made possible through cyclic pressurization. On every flight, the cabin was sealed and pumped to a pressure 8¼ pounds per square inch, greater than the thin air outside. Each climb and descent inflated and deflated the metal tube like a balloon. Engineers at de Havilland knew this would stress the airframe. Before service, they tested a fuselage section by cycling it to a massive overpressure, more than 16,000 times. The structure did not fail. By every engineering standard and mathematical model available to the industry at the time, the Comet was safe. This created a technical mystery. The test structure had survived 16,000 extreme cycles, yet GALYP catastrophically failed in the real world after only 1,290. The Royal Aircraft Establishment at Farnborough, led by Sir Arnold Hall, was tasked with finding the physical mechanism of the failure. Hall's team was given a direct mandate: identify the flaw, regardless of the cost. They built a massive, custom-designed water tank to hold an entire donated Comet airframe, the GALYU. The wings were removed, and the fuselage was completely submerged. Engineers filled the cabin with water and used hydraulic punts to raise and lower the internal pressure, simulating one flight cycle after another at 8¼ pounds per square inch. Water was chosen because it does not compress. If the metal skin failed under pressure, it would not cause an explosion. It would merely leak. This allowed the team to find the failure without destroying the evidence. On June 24, 1954, after 3,057 simulated cycles, the test airframe finally split open. Because the fracture was arrested by the water, the engineers could finally examine the microscopic metallurgical evidence at the exact point where the metal began to tear. Popular accounts often blame the Comet's square passenger windows for the crashes. This is a historical myth. The fracture in the Farnborough tank did not start at a passenger window. It began at the corner of a small rectangular cutout on the roof of the fuselage, which housed an avionics antenna. When investigators examined the wreckage recovered from the Mediterranean, they found identical evidence. In both the test tank and the wreckage of GALYP, the catastrophic tear originated at a single countersunk rivet hole at the corner of that roof cutout. Once a microfracture at that hole reached a critical length, the massive internal pressure violently unzipped the thin aluminum skin. The entire fuselage failed instantly, and the tail section came off in seconds. The aircraft failed because of a hyper-localized millimeter-scale vulnerability, a geometric flaw that was effectively invisible to standard inspection protocols. Using microscopes, investigators discovered that the rivet holes around those cutouts had been punched through the metal rather than drilled. Punching was a fast, cheap manufacturing standard. It had been used for years on unpressurized propeller aircraft where the stresses were low enough that it never caused an issue. As this comparison shows, a drilled hole leaves a clean edge. A punched hole is much rougher, leaving microscopic tears and notches around the rim of the aluminum. On a pressurized jet, these tiny defects concentrate stress. Every cycle of the cabin, those microscopic notches amplified the load in the surrounding material by a factor of 3 or 4. This explains the discrepancy in the numbers. GALYP failed at 1,290 cycles, while the test ship survived for over 3,000. Because the severity of these microscopic notches varied from hull to hull, fatigue life was not a fixed constant. It was a probability distribution dictated by how roughly a factory tool punched the metal on a given day. The Comet had been certified under a philosophy called safe life. This was the assumption that if the overall stress was kept below a certain threshold, the metal would never break. The Farnborough data proved that for pressurized jets, safe life was mathematically insufficient. It could not account for microscale stress concentrations. It was replaced by the fail-safe philosophy. Instead of assuming a structure will never break, fail-safe design uses segmented load paths and tear straps to arrest a crack before it can trigger a catastrophic failure. Modern aerospace engineering assumes that cracks will eventually initiate. The structure is designed to hold the load long enough for inspectors to find them. Farnborough forced engineers to separate crack initiation from crack propagation, turning a mystery into a mathematically predictable discipline. The Cohen inquiry report, published in February 1955, found that the de Havilland engineers were not negligent. They had simply worked at the edge of human knowledge, and the aircraft itself revealed what that knowledge was missing. These lessons were immediately adopted by competitors. The Boeing 707 featured thicker skin, rounded cutouts, and separated engine pods, all based on the new math of fatigue. The meticulous, data-heavy reporting style invented at Farnborough during that summer also became the standard format for every modern aviation incident report used today. If you value this kind of patient, source-based forensic engineering, please subscribe. You can explore our existing case files on the Tenerife collision and the Vigilant Dam right now. The safety of every modern commercial flight exists because a generation of engineers systematically reverse-engineered a tragedy inside a water tank in southern England.